Hello and welcome back to the course on blockchain. And today we're talking about the nonce range. So what do we know about the nonce so far? Well, we know that it's a field in the block which allows miners to participate in the cryptographic puzzle challenge. And how's that? Well, miners cannot change any of these fields except for the nonce, and therefore they have to variate the nonce in order for all of this to change and for the hash to change. And by varying the nonce, they vary the hash, and they hope to get a hash below a certain target. As soon as that happens, then they win the puzzle and they can add this block to the chain and they get the reward. And so that's what we know about the nonce so far, but here's some additional information. The nonce is not infinite. We cannot keep incrementing the nonce forever. The nonce is a 32-bit number, meaning that there's only 32 bits of memory allocated in every single block for the nonce. And to illustrate that, that means that the nonce is an integer which has a range. It can only be anywhere between 0 and approximately 4 billion. So the nonce has a limit, has a cap of 4 billion. And that's very important. And for those, just a quick side remark, for those of you who are techies out there, who are programmers, it's a 32-bit unsigned integer, meaning it doesn't have a sign at the start, and it can, therefore, it's not, usually 32-bit numbers are up to 2 billion, but here it's up to 4 billion because it doesn't have a sign. Anyway, so the conclusion here is that the nonce has a cap. It can only go up to 4 billion. And you might be thinking, well, Kirill, that's very interesting, good trivia fact, but why is that important for us? Well, let's have a look. Let's do some estimations. And we've already done the first part. We've done the difficulty estimations, but practice makes perfect, so let's do them again. Total possible 64-digit hexadecimal numbers that exist in the world is 16 to the power of 64, approximately 10 to the power of 77. Then total valid hashes with 18 leading zeros, assuming the current difficulty of 18 leading zeros, 16 to the power of 64 minus 18, approximately 2 times 10 to the power of 55. And that means, as we discussed previously, probability that a randomly picked hash is valid or will solve the cryptographic puzzle is the second number, the valid hashes divided by the total number of possible hashes, and gives us 2 times 10 to the power of minus 22. Remember that very, very small percentage. This is the likelihood of you solving a cryptographic puzzle if you pick a random, just pick a random hash, or that's the same as saying if you pick a random nonce. Okay, so we're going to underline this number because we'll need it in the next calculation. Now for the nonce, right? So now we know additional information about the nonce. Let's plug it in here. The nonce is a 32-bit number. The max nonce is 2 to the power 32, approximately 4 billion. So let's round it to 4 billion. And we'll underline that in green. And so this is the important part. So the question we're trying to answer is the nonce enough to brute force with 100% certainty our hash, our puzzle? So assuming no collisions, meaning that all of these are going to generate unique nonces, unique hashes. This means that there will be 4 times 10 to the power of 9 different hashes from the, if you go through the whole nonce range, you try every single number in that, among those 4 billion, you will end up trying 4 times 10 to the power of 9, so 4 billion different hashes. And so the probability that one of them will be valid, just one of them will be valid, is if we take this and we multiply it, so that's all the hashes that we try, and now we multiply it by the percentage likelihood of one of them becoming valid, and there we go, we multiply it by that, and we get 8 times 10 to the power of minus 13, approximately 10 to the power of minus 12 if we round that to 10, and that gives us 0.0000000001% chance. So it is tiny still. So basically, even if we go through the whole range of the nonce from 0 to 4 billion and something, if we go through the whole range of the nonce, we will still, this is still the likelihood that we will find a solution to our cryptographic puzzle. So the conclusion here is that one nonce range is not enough. That even if you go through the whole nonce, you are very still unlikely to find the golden nonce, a golden nonce. And yeah, so this puts everything we've been discussing before under the magnifying glass. It puts so much doubt, instills so much doubt in us right now, right? Like, can you feel it? That before we were pretty confident that, like we're just going through the nonce and then and then we will find a hash solution to our puzzle. So let's go here. So we were going like, okay, so we're just going to iterate the nonce. Eventually we'll find the hash. But now all of a sudden we got, first element of news that we got is, well, the nonce is only limited up to 4 billion. So there's not much, you can't go really far, only up to 4 billion. And the second information that we derive now is that the nonce is actually not enough. So that 4 billion is not enough. So does that put the whole cryptographic puzzle under question? Is there even a solution if the probability is this small that we will get a solution? Then what's the point of trying to solve it? What's going to happen when we get to that 4 billion? And like what's a new world look like? Well, let's say this first thing, that a modest miner does about 100 million hashes per second. That's like not the fastest, not the slowest type of mining rig that you can get. 100, quite modest, 100 million hashes per second. It has 100 million different hashes are tried, and that means 4 billion. Or 4 billion hashes, that 4 billion iterations of the nonce that you can have, will be done in, if you divide 4 billion by 100 million, it'll be done in 40 seconds. So what does that mean? That means like in 40 seconds, we will be done, if we have this miner, if we buy this miner, in 40 seconds, we'll be done with the whole nonce range, and then what? And that's the end, right? Nothing, we can't do anything from it. Well, not exactly. And here, everything is thought through. Here's where we introduce a new field again. In reality, there's an extra field, which we haven't talked about yet, and it is the timestamp. It is the timestamp of, when this block is being mined. And the timestamp updates every single second. So here I wanted to show you a website. So if we go here, time.is/Unix time now with capital U, this is the current Unix time. And what the Unix time is the number of seconds that have passed since 1st of January 1970. So this is how many seconds have passed since then. And so this is a time that's often used in computers and programming and so on, because it's so convenient, it's pretty much universal. And so if we go back here, that's the Unix timestamp, and it gets updated every single second. So what that does for us is it creates a loophole. It creates a solution to our problem. Meaning that every single second, this information in this block will be updated because the timestamp will increase by 1 second. And as we remember from the avalanche effect, the hash, even if we don't change the nonce, even if we don't change anything, the hash, if we rehash that, it will be absolutely different. So we know that, and therefore what that means, if we illustrate it, is that if we draw our nonce range here from 0 to 4 billion, and then we put a timer, so we only have 1 second. So basically we have 1 second to go through this nonce range before the timer updates. So what happens is we go through the nonce range, bam, 1 second passed, we only got that far. So we tried all those nonces, none of them matched, we didn't get a hash, most likely. And what happens next is time updates. So a new second, and that means all of these nonces are valid again. This is the important part. All of these nonces are again valid, we can try them again because the information inside has changed, even though it's changed by probably like 1 bit in here in the timestamp, it still has changed. So at least one tiny thing. So every single nonce now can go into this block again, and we can try it again. So there we go again, boom, another second pass, boom, another second pass. And you can see that this miner is going in, it's doing different ranges every time. I just did that for illustration. Usually it'll be approximately the same range, unless it's like overheating or or too cold or whatever. But the point is here that you can see that every single time we go through a certain number of nonces, and then the timestamp gets updated. So what I wanted to point out, it's not a bad thing that we never get to these end nonces. It doesn't matter at all. It's actually a good thing that we have an opportunity to reuse the nonces that we reused. Otherwise, if this wasn't updating, if there was no timestamp, we'd just get to the 4 billion, we wouldn't find a hash, and then we'd have nothing to do. But because the timestamp is updating every second, and it takes this miner 40 seconds to do the 4 billion, well, this is actually generous. So this should be like 1/40th from here to here. This purple thing should be up to 1/40th, like tiny. But for illustration purposes, so here, maybe this is a more efficient miner. And so basically what that's showing is that, again, the timestamp is updating. We're going through as much as we can of the nonce. Timestamp updated. Okay, cool. We can start again and start again and start again. And so that gives us an effectively infinite number of combinations of timestamp plus nonce that we can go through and get the hash. All right, so that's really cool. That solves the problem for one miner. For one miner that's doing 100 mega hashes per second, 100 million hashes per second. Okay, but how about a mining pool, right? What about a mining pool? So let's have a look. Will that solve the problem for a mining pool? If we go here, data, and we go to charts, and we go to hash rate. Okay, sit tight on your chair. Don't let this knock you off your feet. So the current hash rate looks like it's 25, right? 25 million. 25 million looks like it's 25 million hashes per second. No, this is the current hash of the whole network, and the current hash of the whole network is shown here in terahashes per second, trillions of hashes per second. So the current hash rate of the network is eventually we eventually will find the hash, but the current hash rate of the network is 22 million trillion hashes per second. I'm going to say that again just because it's such a cool number. 22 million trillion hashes per second. That's how much the hash rate is now. By the way, you can check it out for all time. You'll see how it's changed throughout history. Like 22 million trillion hashes per second. They will, like, of course they're not all working together. A lot of them are competing against each other. But even if we go to go here back to charts and we find the hash rate distribution, we know that BTC.com is 27% of that 22 million trillion hash rate per second, right? So basically, even if we take this one via BTC or slash pool, 10%, right? 10% of 22 million trillion hashes per second is 2 million trillion hashes per second. So basically, that slash pool will smash through that nonce range in no time, like in 0.000 something seconds. They will smash through it super quickly. And so what we discussed here, if I go back, this solution that it takes us 40 seconds to go through the nonce and we only have 1 second until updates, it works for one miner, but it's not a solution for a mining pool. The mining pool will be gone through the nonce even before the second, even before like this clock has barely started, it will be already gone through the nonce. And so that begs a question: what is the solution for a mining pool? How does a mining pool approach this problem? Because if the mining pool goes through the nonce from 0 to 4 billion like that, I'm trying to click my finger, goes like super fast through 4 billion, and then they have to wait until this updates, until the second is over, until they can do it again. Then there's so much wasted capacity. They're just like sitting idly doing nothing. And that is not acceptable. That's not how the system should work. It shouldn't have that constraint. So that's the question for now. And that's the question we're going to answer in the next tutorial. I hope you enjoyed this one. It's pretty interesting stuff. Like, we're slowly building up on our knowledge. So nonce, timestamp. Next one we're going to add some more. Hope you're enjoying this quest into the world of blockchain and Bitcoin mining. And yeah, next tutorial is going to be fun. We're going to learn how mining pools, how architecturally this problem is solved, that even mining pools can participate and without any constraints. How this constraint is actually not error constraint. There's something else that we haven't discussed yet that helps avoid this constraint. All right, so on that note, thank you so much for being here today, and I look forward to seeing you next time. Until then, enjoy blockchains.